Alright, so this is just me a really brief introduction to pointers. So pointers are just another type of variable. So they basically allow you to access variables beyond their normal scope and allows for functions to directly modify existing variables. So for example, if we have an integer called a equals 5, an integer named a, and we set its value to 5, we can have another variable, we can have a pointer point to this variable. And basically the variable pointer itself, or here I'll name it PTR here. So basically we declare a pointer by specifying a star in front of the variable name. And basically we can have the variable PTR point to a. And the way we do that is by typing an ampersand in front of the variable name. So in this case, remember PTR is a variable itself, except it is a pointer. It stores a memory address to an integer here, as specified here. So basically, PTR point is a memory address to a, and we can have a short little memory diagram here. So here we set a to 5, and pointer, the value of PTR itself is just a bunch of hexadecimal stuff. All you need to know is the memory address of the variable a in like the heap or in the stack or whatever. And when we access this memory address, we're accessing the same variable here. So if we have a printf %d \n just to print out a, we would expect for this to print 5 here. However, if we access the memory address stored by the variable PTR, then we would also get the same. We would get the same value because we're pointing to the same memory location. We're basically pointing to the same variable, which is a. So we just do that by star PTR, and just to demonstrate what the value of PTR itself is, %p \n. So basically, as you can see here, a itself is 5 because we declared it here, and then we set the variable PTR, which is a pointer, to be the memory address of this variable. And then when we access the memory address by specifying a star in front of PTR, which is called dereferencing, then we get this and we print it out. We get the same variable here. And just to show the memory that PTR is not an integer, but instead a memory address, that's this. And when we modify PTR, say we do something that let's say we dereference PTR. Basically, we're getting this same variable. If we modify this, if we dereference PTR and set that if we modify the value stored at this memory address to something like, I don't know, 2, and then we do the same thing. We see that because we're accessing the memory address stored at PTR, which is the same as accessing a, and we set the value of at this memory address to 2, we are also setting the value of a to 2. And as you can see, the memory address, we're just accessing this memory address and changing its value to 2, which is the equivalent of overriding a. And yeah. Now, one application of pointers is that you can access memories beyond access variables beyond their normal scope. For example, say we have an integer here, a in the main method here, and say we want a method that just adds 5 to it. So normally in something like Java, you would have you instead set a to add 5 a here. So basically, add 5 here, the function, it basically returns the variable plus equals 5, and we basically overwrite the integer a here with that. So I screwed up my tabs. So as you can see here, we're basically just overriding the value a, but we can actually directly modify a with the function with a function here instead of overriding it with return types, because it can get messy sometimes. So instead we can modify this function add 5, and instead of we can get rid of this return value here because we're switching to void here. So we can do this by changing the parameter here. Instead of having it having a parameter just be an integer, we can have it be a pointer to an integer or a memory address of an integer. And then we can just basically just dereference this. So basically, think of var here is just a pointer. It's just another pointer from before. And we can just basically overwrite the memory address stored by var here, and add 5 to that. So we can just do star var plus equals 5. Basically, we're getting, so in this case here, we're say we want to add 5 to A. We add 5 to A by passing the memory address of A here. And then we, by passing the memory address here, we're basically setting the pointer var to point to the variable A here. So when we dereference var, which is basically just accessing the same variable A here, and add 5 to it, we are modifying A and adding 5 to the variable A itself. So when we see here, we write to it and make, we get the same result because we are basically passing the variable A by reference technically, but it's really just pointer shenanigans, and we're dereferencing variable, dereferencing var, and adding 5 to it, adding 5 to the integer at the memory location stored by var. Okay, so far in C we've learned how to basically create variables, but what if we need to create an unknown amount of variables, such as nodes in a linked list? Then what do we do? So in that case, we'll need to do what's called dynamic memory allocation, and which really can only be done with pointers here. So let's get up here. So the way we dynamically allocate memory in a program is by calling malloc or free, and or by calling malloc or calloc. What am I saying? And these two functions are both part of the standard library here. So for example, say we have a pointer to an integer called pointer, but we don't have an integer to point to. So the way we can do that is by creating a new by allocating space in the heap for a new integer by calling malloc. So a malloc here is a function that allocates the number of bytes you specify, and then it returns the memory the beginning memory address of the memory it just allocated. So in this case, malloc, we want to malloc enough bytes for an integer, so size of int. So in this case, we basically give pointer an integer to point to, and this integer is stored in as a part of the heap. And there's also calloc, but I won't be going into that too much. So in this case, malloc allocates enough space for an integer on the heap, and the variable ptr, which stores a memory address, is set to the memory address of the integer or of the memory block we just allocated for the integer. So then we can just give pointer a value, say 5, or give the new integer we just created with malloc, or space for integer with 5 or something, and then we can just do printf here. So we basically just allocate memory for an integer on the heap, and yeah. And however, it's unlike Java, where if you once you're done with a variable and you just and you don't have any more ways to reach that variable, we have to actually call Java basically handles variables that you can't access with its garbage collector and automatically deallocates memory. But unlike Java, C, whenever you dynamically allocate memory in C, you have to free up the memory you just allocated yourself. So in this case, we call malloc for an integer, and we allocate memory for an integer for this pointer here. So let's do this. Make. So here we allocate memory for an integer, but the thing is here we don't free up this memory. So we basically have what's called a memory leak, and the way we can solve this is with the free function. So before we get onto that, I'm just going to demonstrate what how we can find memory leaks in a program. Yeah, we do that with a program called valgrind, and that's the wrong one. Crap. Where is that? So with Valgrind, we can basically find if there's any memory leaks in our current program, and we can also see what is it? Where that memory leak happened. So in this case, we allocated some memory for a pointer, but we never deallocated it. So we can call Valgrind on that. Well, we'll figure that out later in CSE 30, I think. And once Valgrind is running, as you can see here, there's 4 bytes for an integer because integers take 32 bits here, which is 4 bytes because each byte has 8 bits, yada yada yada. And as you can see here, 4 bytes were never deallocated, and we have a memory leak. And what Valgrind does, it helps you helps you find where that memory leak occurred. So in this case, it says it occurred in the main function at at line 5. So if we go up, go to line 5, we find a memory leak occurred here. So we never freed up this this block of memory. So the way we do that is by calling free. Free is is another function that basically you pass in a memory address that for something you dynamically allocate memory for, and it deallocates that memory. So basically, it gets rid of the memory leak. So what you want to do with free is you pass in the starting block of the memory block you allocated originally. So in this case, pointer is set to the beginning of this memory block here, and we want to pass in the memory address PTR to free it. So we call free on pointer, which is we free the memory block we allocated, and we basically just use that to deallocate the memory. And as you can already see here, we can run make, recompile it. There, as you can see, all the memory blocks were freed. There are no more memory leaks, and you will probably pass more autograder tests and stuff. And yeah.